Hi everyone, my name is Youssef Housni, and I'm a second year PhD student in the GRACE team within École Polytechnique and INRIA. My presentation is about a joint work with Aurore Guillevic, who works at INRIA Nancy. So the paper title is Optimized and Secure Pairing-Friendly Elliptic Curves Suitable for One-Layer Proof Composition. So very simply put, we propose a new pairing-friendly elliptic curve that is suitable for a very specific problem that we explain. So we put this into context. So this is the context of zero knowledge proofs, ZK-SNARKs, proof composition theory. And then we will present this work, which is this new elliptic curves, both from a theoretical point of view, but also from an implementation point of view. And we will end the presentation with some applications that already use our work. So a zero knowledge proof is a proof that is sound, complete, and zero knowledge. Sound meaning that there is no that a cheat prover cannot convince an honest verifier. Complete meaning that an honest prover convinces always an honest verifier. And zero knowledge property means there is no information leakage beyond the fact that the statement is true. So as a subset of those zero knowledge proofs, there is what we call ZK-SNARKs, which stands for zero knowledge succinct non-interactive arguments of knowledge. So those are zero knowledge proofs, means that they are sound, complete, and zero knowledge. But also, additionally, they are succinct and non-interactive. Succinct means that the proof is very short and easy to verify, informally put. And non-interactive meaning that there is no interaction between the prover and the verifier throughout the protocol. So arguments of knowledge, this is a relaxation of the proof notions, meaning that the soundness is only computational. So as a subset of those ZK-SNARK, this is what we call pre-processing ZK-SNARKs of NP language. So this means that we need a pre-processing phase, and we are proving statements about non-deterministic polynomial language. So let's put things a bit formally. So we have a public NP program, F. We have public inputs X and Z, and we have private input W, such as the relation Z equal to f of x and w is satisfied. So a ZK-SNARK consists of three algorithms: set up, prove, and verify for some security parameter lambda. So the setup is actually trapdoor, means that we need a secret to security parameter lambda and the public input f, and we output some key material, so pk as in proving key and vk as in verification key. So the prove algorithm takes the public inputs x and z and the private inputs and the proving key. So it takes basically everything in order to prove that the statement is true. So it outputs a proof denoted pi, and the verify algorithm takes the public input x and z, the proof generated pi, and the verification key vk, and outputs some boolean whether the proof is verified or not. So the setup can be generated by anyone as long as it is a trustworthy party, because it is a trapdoor setup with some secret door that can break the soundness. And the prover is by the proof algorithm is by Al is the prover, and the verifier by Bob, the verifier. So by anyone basically who holds the verification key. So this succinctness, which defined as the key property, is a proof that is short and easy to verify informally. So if we are given some formal definition, we would say that a succinct proof pi has a constant size with respect to some security parameter, and that can be verified in constant time with respect to the public input size. So this is the definition from a paper BCTV 14 due to Ben-Sasson, Chiesa, Tromer, and Viesa. So there are many definitions of succinctness. It depends on the paper and the system being pushed for, but this is somewhat the ideal definition of succinctness. So we've been talking about zero knowledge proofs, ZK-SNARKs, and pre-processing ZK-SNARKs for NP language. So we will be focusing on what we call pairing-based ZK-SNARKs in short, or pairing-based ZK-SNARKs for NP language with this pre-processing phase. So in those type of ZK-SNARKs, we need a pairing, which is a special operation. So we need a pairing-friendly elliptic curve. So we define an elliptic curve in this slide with its short Weierstrass form. y squared is equal to x cubed plus ax plus b defined over a finite field q of with q a prime power. So the cardinality of the elliptic curve is equal to q plus 1 minus t with t the Frobenius trace. So a prime divisor of this cardinality is denoted r. Capital D is the complex multiplication discriminant, which verifies the complex multiplication equation. 4q is equal to t squared plus d times y squared with y some integer. Small d is the degree of the twist, k the embedding degree, which means the smallest integer such as r divides q to k minus 1. We have three groups of order r, g1 and g2 over elliptic curves, and gt, which is the authority of unity. So we have basically a pairing which goes from g1 times g2 to the target group gt. So those are the classic notations of pairing-based cryptography that we will be needing in the sequel. So those pairing-based ZK-SNARKs, here in this slide we give an example, a concrete example of such a construction due to growth in 2016. So commonly referred to as growth 16 in the literature. So this is the state of the art, by the way, with respect to this key property that is succinctness defined as in BCTV14 paper. So we have a public program F, so an instance of a public program F, so we denote phi. So we have our algorithms that we proposed earlier, setup, prove, and verify. So the setup takes F, tau, and lambda, and outputs the PK and VK. So here we give explicitly the verification key, as we will be focusing on the verification side later. So the verification key is a set of elements in G1, G2, and GT as defined in the pairing notation slide. The proof algorithm takes the public key, the private input, and the instance of the NP program, and the output are proof by which is three elements, A, B, and C, in G1 and G2. So we see that it is constant size with respect to the security parameter lambda that defines G1 and G2. And the verify algorithm is actually equation 1, which is a pairing product check. So so the verification takes the proof, which are A and B, A, B, and C elements in G1 and G2, and the verification elements, and verifies this pairing product equation. Note that VK sub X, so this verification key, is a multi-exponentiation or a multi-scalar multiplication in the group of elliptic curve points of size L, which is the size of phi that is the instance of the public input. So this multi-exponentiation is constant time with respect to the public input, which means that this equation 1, which is the verification equation, is constant time with respect to the public input. So let's motivate a bit this work. So we said that we are proposing an elliptic curve for ZK-SNARK or for a specific problem in ZK-SNARKs. So our curve is actually used in industrial applications, so in the blockchain space. So very quickly, a blockchain is a decentralized, transparent, immutable paying ledger. Transparent means that everything is visible to everyone. Immutable means that nothing can be removed once written. And paying that means that everyone should pay a fee to use this blockchain. So this transparency results in a confidentiality problem. ZK-SNARKs can be a solution because those are zero knowledge proofs. Immutability results in scalability problem. This can also be solved with ZK-SNARK somewhat because the proof is constant size. And paying result in a cost problem, and this also can be somewhat solved with ZK-SNARKs because the verification in our case is constant time with respect to the public input. My question is, how much does it cost in space and fees to verify, let's say, 1,000 proofs? So the problem is, to solve this, we can maybe aggregate those proofs. So can we aggregate 1,000 proofs into a single constant size proof? Can we verify 1,000 proofs at the cost of one proof? Can we do both? So the answer is somewhat yes. The idea would be, since we are working on zero knowledge proofs for NP language, we can observe that the verification algorithm, which is equation 1, which is this pairing product check, is also an NP program. So we can generate a new proof that verifies the correctness of the previous 1,000 proofs. And since the proof is constant size and the verification of this proof of proofs is constant time, then we answer these two questions basically. So here I propose two scenarios. First, the number of proofs to aggregate is not fixed. So we do not know how many proofs we want to aggregate, so we need to aggregate proofs on the fly. And the second scenario would be that we aggregate only once since the number of proofs is fixed. Let's see the technical side or the arithmetical side of things. So we said that this equation 1 can be expressed, can be seen as an NP program. So it can be expressed as an instance of an NP program. But how easy or difficult is this can be done? So remember that the verification algorithm, equation 1, sits in FQ2K because those are involves pairing operations. But the generation sits in FR, which is the subgroup order of the elliptic curve. So remember that Q is the field size of the elliptic curve and R is its prime subgroup order. So we have a mismatch of arithmetics. So the first attempt would be to choose an elliptic curve for which Q is equal to R, but this is unfortunately impossible for pairing-friendly elliptic curves, and for ordinary elliptic curves, the discrete logarithm is trivial. The second attempt would be to simulate FQ operations, so via FR operations, which boils down to simulating the verification algorithm as an instance of an NP program to generate a new proof. But this, although is possible, results in a huge overhead. The third attempt would be to use not only one elliptic curve, but maybe many elliptic curves in a way that we create the first 1,000 proofs, let's say, on a first system initiated with an elliptic curve, and then we create the second proof of proofs on a different elliptic curve that solve this arithmetic mismatch. So this is what we call cycles or chains. This was introduced in the same paper BCTV14 and then relaxed by the notion of chains in the paper referred to as ZK due to Bow, Chiesa, Pratiush, Misha, and others. So formal definition of an M chain. So we have distinct elliptic curves, M elliptic curves, E sub I, defined over finite field FQ sub I, such as the subgroup order of an elliptic curve is equal to the field size of the previous one, and so on and so forth. An M cycle is an M chain for which it has this additional property. The subgroup order of the first elliptic curve is equal to the field size of the first one, or of the last one. So we have this cyclic notion. Here we propose some elliptic curves in the literature. So MNT4, MNT6, those are first implemented in LibFF. So we see that the field size of one is equal to the subgroup order of the other one, and vice versa. We have MNT4 753 and MNT6 753. So this is the same elliptic curves but with different parameters. And then we have the BLS12 377 as an inner curve and CP6 as an outer curve of a two chain. So the CP6 subgroup order is equal to the field size of the inner curve BLS12. So our work is proposing a new outer curve to the same BLS12 377 elliptic curve. So let's take a look at the parameters of those proposed elliptic curves. So we'll be going very quickly through the MNT4, MNT6 constructions because those are cycles. What we are interested in is the chain. So the cycles, we have two kinds of cycles, one with low security level but with small parameters, and the other one with standard security but with big parameters. What we are interested in is the cycles, is the chains. So the chains, we have the inner curve, the BLS12 377, defined over a field of 377 bits, a subgroup order of 253 bits, an embedding degree k equal to 12, a twist degree 6, a coefficient a and b 0 and 1, and standard security 128. So this is somewhat the state of the art of pairing-friendly elliptic curves, right? The outer curve CP6 proposed in this paper ZK is defined over a field of 782 bits, subgroup order of 377 bits because it is equal, by the way, to the field size of the previous BLS12 curve, an embedding degree 6, twist of degree 2, coefficient A of the curve equal to 5, and B is very big. Security 128. Our work is proposing an elliptic curve defined over a field of 761 bits, same subgroup order as the CP6, embedding degree 6, 6 twist, coefficient A 0, B minus 1, and 128. We shall show that this construction benefits or enjoys very efficient properties when it comes to implementation. So let's take a little bit a look to the big picture. So we are doing SNARKs. We need pairing elliptic curves. So if we are just doing SNARKs, we need this elliptic curve to be pairing friendly and the subgroup order -1 divisible by a high power of 2. So this is to have efficient FFT implementation. So we can choose from a wide range of elliptic curves in the literature, namely BN, BLS12, BW12, maybe KSS16. If you want to do, however, recursive SNARKs, so remember those two scenarios with 2 cycle or 2 chain. If you want to do 2 cycles, we need 2 elliptic curves, both pairing friendly, for which the subgroup order of one is equal to the field size of the other and vice versa, and all the parameters should be highly two-adic, so namely R sub 1, S sub 2, Q sub 1, Q sub 2. So unfortunately, the only construction that we know of from the literature is MNT4 and MNT6, and there is a paper due to Chiesa and others, CCW19, that establishes mostly a negative result in order to find other cycles. However, if we want to do the scenario with the 2 chain, then we need 2 elliptic curves, but in this case we can create or construct those 2 elliptic curves in a sequential fashion, meaning that we have all the flexibility to construct a pairing friendly elliptic curve, which is the inner curve. So it should be pairing friendly, and R-1 should be highly two-adic. So those are the same requirement as a SNARK friendly elliptic curve. But we need also Q sub 1 minus 1 to be highly two-adic, because Q sub 1 is equal to R sub 2, which is the subgroup order of the next elliptic curve. So this next elliptic curve, namely E sub 2, should be pairing friendly, but additionally it should have a subgroup order exactly equal to exactly the field size of the previous one, Q sub 1. So if we want to detail those requirements for the second elliptic curve, so Q is prime power or prime, T relatively prime to Q, so this is to have ordinary elliptic curves, R prime, R divides Q plus 1 minus T has a theorem, R divides Q to K minus 1, embedding degree requirement, and the complex multiplication equation is satisfied for some small d. But we will substitute 0.3, 4, and 5 by just fixing beforehand the subgroup order R, such as it divides Q plus 1 minus T and Q to K minus 1. So this is done by Cox-Pinch algorithm, which is, by the way, easy to understand. We just start by fixing K and D, and choosing a prime R such as K divides R minus 1 and minus D squared 3 in FR. So this is basically by observing that T minus 1 is equal to Q modulo R, so that we take a generator of FR X and we raise it to R minus 1 out of K, and we take this to be equal to T minus 1. And then everything follows up by definition. The problem with this construction is that the ratio between the field size and the subgroup order is equal to 2. This is basically because Q is a function of T square and Y square, and T and Y are taken randomly modulo R. So one expects that T and Y have R size. The other problem is that the curve parameters are now expressed as polynomials, and for efficient implementations we need polynomial expressions. If we take a look at the literature, breathing wing method is basically a mutatis mutandis translation of Cox-Pinch method into the polynomial domain. So this solves those two problems, but it's maybe not, it maybe doesn't fit our needs to construct these second elliptic curves. Why? So it solves the first problem because we take ty as polynomials modulo another polynomial, so the degree are strictly smaller. So the ratio is strictly smaller than 2. But the problem is, if we take the subgroup or the polynomial of the second curve, the outer curve, to be equal to the field size polynomial of the inner curve, and then we evaluate it at the same seed so that we have this specific value of the subgroup integer, maybe the field size polynomial wouldn't result in primes. So we checked this and it didn't. But before talking about this, just some notes in order to find a better elliptic curve for our problem is, uh, so the group G2 is isomorphic to a group on another elliptic curve defined on a smaller field if we use the twist theory. Basically, it is isomorphic on the R torsion defined over the field, the extension field Q2 K out of D, with K the embedding degree and D the twist degree. So if we want takes the degree of the twist to divide the embedded degree, then one can compress the G2 group. So in Cox-Pinch method, so it's we can choose the embedded degree to be equal to 6 because the inner curve, so BLS 12, has an embedding degree 12 to have a security 128. Since in Cox-Pinch the parameters are twice bigger, then one can just choose the embedded degree to be equal to 6 to meet the same security requirement. But if we fix the complex multiplication to be equal to 3, then we have a 6-tick twist, and then so small d is equal to 6, small k is equal to 6, then we can compress G2 to the base field FQ. Another byproduct would be to use endomorphism-based optimization such as GLV multiplication over G1, but also over G2 because G2 is on the base field. Another note is to restrict the search to a field of size less than 768 bits, because even if the Cox-Pinch result in parameters twice bigger, one should carefully choose those parameters because we implement the finite field arithmetic over the Montgomery domain. So in CP6 curve, they exceeded this Montgomery domain, which resulted in a bigger curve. With respect to the Breising-Weng method, so we chose the subgroup order to be equal to the field size polynomial of the BLS12, but this resulted in a polynomial Q that is reducible, which means that it cannot produce primes. So we tried to lift those polynomials T and Y from the complex multiplication equation in order to fit our requirement and to have Q irreducible, to have primes. So we found an elliptic curve, y squared equal to x cubed minus 1 over a field of 761 bits. So those are the polynomials of our elliptic curves, and we evaluated these in the same seed as the inner curve. We used an M twist for the second curve for the pairing, so y squared is equal to x cubed plus 4. So those lifting cofactors are 13 and 9. So those are the smallest cofactors we found in order to meet our requirements. So let's recapitulate. We found an elliptic curve, an outer elliptic curve for the BLS 377, defined over a smaller field by one machine word compared to the CP6, to the previous state of the art. So we have a G2 group compressed over the base field, so which is a factor 6 compression compared to a factor 2 compression for the previous states of the art. So the curve parameters have polynomial expressions, which means in this case we can allow fast implementation. We found a very efficient optimal 8 pairing, and we had GLV multiplication over both G1 and G2, and also subgroup checks and cofactor multiplication tricks via endomorphisms. And also we proposed, based on the literature, some secure and fast hash to curves for both the G1 and G2 groups. So for the implementation side, so all the operations are faster on our curve, but since we focused our presentation on the verification side of a ZK-SNARK proof, then we will be focusing on the pairing when it comes to implementation. So in violet is the 8 pairing in the CP6 curve case, and in blue is the optimal 8 pairing in our case. So a pairing is, or state-based pairing is basically two operations, a Miller loop and a final exponentiation. So this Miller loop, in our case, we have two Miller loops, but smaller, so than the Miller loop size in the case of the CP6. And the final exponentiation is very fast in our case, since we have polynomial parameters, so we could use these lattice-based optimizations with polynomials. So we showed theoretically that in order to compute a pairing in our case, it costs 4.5 less multiplications in a smaller field by one machine world compared to the previous state of the art. So we also implemented those results in a Rust language in ZK library, so the same library that is used to implement the CP6 curve. So we showed that to compute a pairing, we are 15 times faster and almost 30 times faster to verify a Gore-16 Pro. So there is a mismatch between the theory and the implementation, but this is basically because in this library, the CP6 curves was pairing was implemented with affine coordinates, which are, by the way, in this case faster because we are working in cubic fields and big fields, but the library omitted to implement faster inverse in the cubic field. Some applications that already use our work are Alio, so which are private applications, so proofs of proofs. Celo, which generates BLS signatures and then verify a bunch of these signatures in a proof of proof. And Clearmatic ZK, which is a ZK-SNARK aggregator in Ethereum, and EY Midnight ZVM, which is a private smart contract on Ethereum that hides the function being called in ZK-SNARK. So though all those applications already use our implementation in Rust. So that is for me. Thank you for watching.